to another A-Level Computer Science video with me, Mr Goff, from MrGoff.com. This video will focus on trees. A tree is an abstract data structure that is a special type of graph. To be a tree, a graph must have the following qualities. All nodes must be connected, and all connections undirected. It must also have no cycles. This would be a path that could lead back on itself. It is important to note that not all trees have to have a root. However, the rest of our discussion of trees will revolve around rooted trees. A rooted tree is a special type of tree with the following properties. A root node with no parent node, only child nodes. In this case, A is the root node. Each subsequent node has connections to one parent node and their own child nodes. So B is connected to its parent A and has its own child D and E. Similarly, C is connected to its parent A and has its own child nodes F, G and H. It is important to understand the terminology of rooted trees. A node is a single piece of data in the tree. In this case, each letter is a node. An edge is the connection between the nodes. A root is the only node with no parent, in this case, A. A child is a node that has an incoming edge from a node above. A parent is a node that has an outgoing edge that connects to a node below, or multiple nodes below. It is possible that a node might be both a child and a parent. For instance, D is a child of node B, but a parent of nodes I and J. A subtree is any parent node and all the connected child nodes beneath it. So for instance, B with all of D, E, I, J and K. A leaf node is a node that has no children. A binary search tree is a special type of rooted tree where each node has a maximum of 2 children. To construct a binary tree, you need to follow these steps. Have one piece of data act as the root node. For each new item, the root node becomes the current node. If the new item is above the current node, move right. If it is below the current node, move left. Continue down the tree applying the last 3 rules until a leaf node is found. If the item is above the leaf node, place it below to the right. If it is below the leaf node, place it below and to the left. Let's see an example of how this works in practice. We'll construct our binary search tree from the list Jim, Bob, Sam, Tom, Tim, Art, Joe and Dan. So Jim becomes our root node. Bob comes before Jim, so we go to the left and we add Bob. Sam comes after Jim, so we go to the right and add a new node, Sam. Tom is after Jim, so we go down to Sam. It comes after Sam, so we add a new node to the right of Sam beneath it, Tom. Next we search for Tim. Well, it's beyond Jim, so we go to Sam. It's beyond Sam, so we go to Tom. It's less than Tom, so we would add a new node to the left from the beneath of Tom. Next, we're going to add Art. Art comes before Jim, so we go down to Bob. Bob is its own leaf node, so we add a new node to the left of Bob for Art. Next, we've got Joe. Joe would come after Jim, so we go down to Sam. It would come before Sam, so we add a new node to the left beneath Sam for Joe. Finally, we have Dan. Dan would come before Jim, so we move down to Bob. It would come after Bob, so we add a new node to the right beneath Bob for Dan. There are 3 ways of traversing a binary tree. Each of these will result in outputting the names in a different order. Pre-order traversal, in-order traversal, and post-order traversal. With pre-order traversal, we begin at the root node Moving left, we encounter each node as we pass the left side of that node. So first we encountered Jim, then Bob, then Art, then we move down, around and underneath, and we pass the left side of Dan. We next move up and around, and the next node we encounter is the left-hand side of Sam. Then it's Joe, then we come round to Tom, then Tim, and we've finally finished the entire tree. With in-order traversal, we still begin at the root node and move left, but we encounter each node as we pass directly underneath it. This means the first node we encounter is Art, followed by Bob, then Dan, then Jim, then Joe, then Sam, then Tim, and finally Tom. With post-order traversal, we're still starting at the root node and moving left, but this time we encounter each node as we pass its right-hand side. So with post-order traversal, we encounter Art, then Dan, then Bob, Joe, Tim, Tom, Sam, and finally Jim. A binary tree can be implemented as a 2D array where each array in the array of arrays is a node and contains the array position of its left child, the node data itself, and the array position of its right child. A node value of -1 is used to indicate there is no node in this position. Looking at our example, we can see that in position 0 in the array would be an array containing the data 1, Jim, and 2, indicating that Jim is linked on the left to the data stored in position 1 in the array, and on the right to the data stored in position 2. In position 1, we find Bob, which has got links to, on the left, the data stored in position 5, and on the right, the data stored in position 7. This is Art and Dan. Art and Dan are both leaf nodes with neither left nor right branches, so both left and right are represented by -1 in our array. That brings us to the end of this video on trees. Join me again soon when I'll be back with another video on vectors. Use the resources at mrgoff.com to help you revise computer science. And until next time, it's bye for now.